Colleagues, dear friends, welcome to the Cyprus Institute on this beautiful evening for the 2022 Hubert Curien Memorial Lecture. To start the proceedings, I would like to invite the President of the Cyprus Institute, Professor Kostas Papanikolas, for a few welcome words.
Excellencies, colleagues, ladies and gentlemen, it's a real pleasure to be back in many ways. It looks like, and I hope this is not a premature statement, that this period of isolation, of virtual contacts is over. We're back into real contact, real interaction, real lectures, and what better beginning to restart really these events of the Cyprus Institute of Public Lectures with our gold standard, the Hubert Curien lecture series. Actually, another first is that it's the first Hubert Curien. By the way, this is the 15th Curien lecture. So it's long-running series. It's the first one we are holding in the amphitheater, open air. The previous one generally were done in February in conjunction with the board, and it was in a closed room. But I think most of you'll agree this is a far better venue. We're really privileged to have an extraordinary speaker tonight, Professor Jean-Philippe Boucher. But I'll introduce the lecture series it's in memory of Hubert Curien. I'll say a few words about the lecture series and Hubert Curien, and then we'll have the introduction of the speaker by Professor Edouard Brezen following me. The Hubert Curien, a giant of science, a giant of science policy in every respect of the 20th century era. We were very fortunate that Hubert Curien really played a major role in the establishment and launching of the Cyprus Institute. Actually, this is taken from the invitation, probably which you don't have with you, that you have received, which briefly states a few things and facts about who Hubert Curien was and his association with the Cyprus Institute. Hubert Curien, a physicist, brilliant physicist, but I will not expand on his physics achievements, but rather on his impact on global science, particularly European science. He was twice Minister of Research in France, once under a government of socialists, and one Brocard, which was, let's say, center-right government, which recognized his breadth and acceptance across the society. He was one of the founders, the key probably of many European institutions, the European Space Agency, the Academia Europea. He played a seminal role in the CERN, being president of the CERN Council. He chaired and played a major role in restructuring CNRS, the French, the largest research organization in France, president of Académie des Sciences in France, on and on. One can give a whole lecture about his achievement. It is then really very important to realize how fortunate we were to draw his attention and his help in the establishment of the Cyprus Research and Educational Foundation, CREF, and subsequently Cyprus Institute, where he became the first chair of the board. He played a magnificent role in the design of the blueprint to establish Cyprus Institute from 2001, actually. He participated, and I'll show pictures, in the deliberations that set the blueprint of the Cyprus Institute. And he chaired, actually, the first meeting of the board. Here is a picture of 2002 at the Presidential Palace. You recognize lots of, is who's in, basically half of them, is who's in global science. You recognize two Nobel Prize winners there. Hubert Curien is here, you can see, next to Herbert Schober, next to Jeffrey Sachs, next to President Vassiliou, next to Paul Crutzen, etc., etc. And actually, a quiz for all of you, you recognize out of them 4 Curien lecture speakers in subsequent years. This was the culmination of an exercise to design the Cyprus, what became the Cyprus Institute, and was presented to, we are there because it was presented to President Clearidis at the time, with the presence of President Vassiliou, who was negotiating at that time the entrance of Cyprus to the European Union. And I remember the exchange between Hubert Curien, President Vassiliou, and President Clearidis. And President Vassiliou said, this will be a gift of Cyprus to the European Union. Not a gift of European Union to Cyprus, because it will help as a gateway from Europe to the Eastern Mediterranean and Middle East. And then Hubert Curien said, and we used it ever since, that the Cyprus Institute is a European institution for the Eastern Mediterranean and the Middle East, based in Cyprus. Really, what a concise summary. Then this is 3 years later, 2005, again at the Presidential Palace. The meeting of the first meeting of the board was February 2005, chaired by Hubert Curien, and we were invited to the Presidential Palace. At that time, President, as you see, Tassos Papadopoulos succeeded President Clearidis. Again, President Vassiliou present and connecting with successive governments, and a number of trustees, which you recognize some of them, I suspect. Here is President Vassiliou, Hubert Curien, President Papadopoulos, and Andreas Bouskos, the chair of the executive committee at the time. Again, President Vassiliou, Papadopoulos, and Hubert Curien. And here is, I'll finish with the 14 previous lectures, and really it's a rostrum of most eminent world leaders, scientists, politicians, etc., starting with Jose Mariano Gago, and ending with actually a colleague of today's speaker, Marc Mézard, who honored us in 6 months ago by becoming a trustee of our board. Apparently, the visit here helped convince him to lend his considerable talent to that. Hubert Curien left a legacy, not only his empowering us with that, he left a legacy that helped us recruit the successor to him to chair the board. We thought, what do we do after Hubert Curien? What can we do? Well, the board said, why don't, it's the obvious, who succeeded him in the academy, who succeeded him in CNRS? And they said, of course, Edouard Brezin. So the sequence, the baton was passed to another giant of European science, Edouard Brezin, whom is with us today to introduce the next Curien lecturer. And thank you for your patience, but I think we owed this tribute to Hubert Curien. Thank you very much.
So you already know who's our next speaker. I'd like to invite Professor Edouard Brezin, who's not only the former president of our board, but of course the former president of the French Académie des Sciences and a professor at the Ecole Normale Supérieure, to introduce our speaker.
Thank you.
Yeah.
Thank you. Before telling you, improvising about Jean-Philippe Boucher, I want to add two small things that you could add to your list describing Curien's achievements. In 1944, he was 19. He was a student preparing the schools of Ecole Normale Supérieure, from which he graduated. He left it and he joined the underground in his area, east of France, where he fought, and he was wounded there. He was wounded, and he always say, joking, that this is why he chose the École Normale rather than the École Polytechnique, and because of that. That's one thing. Another thing which I remember, which was very important for us in Paris, it was in the 90s. I mean, it's so important because it's repeating now. In the 90s, a lot of former Soviet scientists were trying to survive after the fall of the wall and the terrible economic condition for scientists at the time. And there were several attitudes in the world. Some countries decided, oh, let's import them, it's cheap. And some, with Curien, we discussed, and the idea was maybe we could help to survive in Moscow, St. Petersburg, and spend 6 months out, and that would help them to survive. So we had an agreement at the time with the famous Landau Institute, and that's because Curien's understanding. Nowadays, we still have programs to help scientists in exile, but we are totally flooded by both Ukrainian and Russian who have signed very courageously a petition against the war, very clear, at the end of February, and they are now in trouble for obvious reasons. But we are here. First of all, let me say how happy I am to be back, because you look much better than in Zoom, and, and that's a pleasure. It's also a pleasure to introduce my friend, colleague, Jean-Philippe Boucher, that I know for many years. It's not easy to introduce him because his life is not quite simple in terms of science. He studied at the École Normale, like Curien, like many, and graduated as a physicist, did a PhD in physics. But scientists split between two kinds. I'm making things very simple. Some are reductionists. In other words, they want to know how matter is made, how atoms is made, everything. They want to look inside. Some other are looking at large system, collective behavior of large assembly of atom, molecule, constituent. And Jean-Philippe belonged to that school, which is called statistical physics. It's statistical because the systems are so big that you cannot follow every constituent, but there are well-known statistical methods to follow that. So this is how he graduated and how he made early contribution to the field, like, I don't know, I mean, many are new. I will bore people if I tell you that he had made important contribution to anomalous diffusion in disordered media and things like that, which are very well known in the field. After some time, he moved to the CEA. I don't know if CEA initially, when I was there in my early days, was a Commissariat à l'énergie atomique. But very clearly they changed CEA into Commissariat aux énergies alternatives. So Jean-Philippe was there, and he was doing physics all the time, statistical physics of disorder system, but he regarded statistical physics as a way of looking at the world much beyond standard physical systems. In particular, he was one of the early pioneers of what is called econophysics. The idea is that Jean-Philippe will expose is that when you look at, I don't know, financial market, the economy in general, it's full of many components and full of fluctuation, very much like what happens in matter. So Jean-Philippe will tell you what he did with that, but remarkably enough, he succeeded during all this time to remain a physicist, an econophysicist also, which some of my colleagues, strict physics, insisting on physics, didn't want, but finally he was accepted as for this. And an event happened, unfortunate, which led by necessity the death of someone that Jean-Philippe was advising, and he had to take the responsibility of a firm which is called Capital Fund Management, I think, CFM. You will see that in the introduction. So now his life, I don't know how he manages. He teaches at the Ecole Normale. He writes books. For instance, this year he has written a book on random matrix theory, which is clearly a mathematical subject. At the same time, he manages this large company now, which has succeeded to attract a lot of physics and mathematics PhD who, rather than going to standard academia, have been working with Jean-Philippe. So I am very pleased that he has chosen, that he has accepted to give this Curien lectures for all the reasons that I mentioned. I think they are original. He's not an economist in the standard acception of what economics are. Some are worried even that statistical physicists claim that they can bring something by looking the way physicists looks at matter. He looks at market, at fluctuation, at the economy in a completely different way, and therefore I look forward to his presentation here. So Jean-Philippe, thank you for being here.
So we'd like to invite Professor Bouchaud for the Hubert Curien lecture this evening. Thank you very much.
Well, thank you very much for the invitation. I feel extremely honored and somewhat flustered, actually, to give a talk in front of you in such a beautiful setting. And I realize how these Hubert Curien lectures have been important and full of very prestigious speakers. So I hope I'll be up to the task tonight. Just a few comments on Edouard's presentation, which was very, very kind, and thank you very much for that. Actually, I've been involved in CFM for longer than that, and Jean-Pierre Aguilar's death in a glider accident in 2009 accelerated the whole thing, but it actually was preceding this. So I came into this field through statistical physics, as it's been said, and I'm going to explain why. And I also came into this field through financial markets, because capital fund management is an asset manager. So we are every day trying to invest in the markets and trying to understand how markets behave, how markets function. And I think what's original with our company is that we're trying to remain at the border between academia and the professional activity. So we're in a position which is unique, because we can look at the data, and the data tells a lot about human behavior and how to model human behavior, and that's what I want to convey tonight. So, as I said, my inroad into this field is through financial markets, and maybe what will be surprising to you, or maybe not, is that if you look at the history of financial markets, it is strewn with crashes that we know, but what is strange is that many of these crashes don't have a plausible cause, actually. So, for example, 1929, one of the biggest crash in the 20th century, but also 1987, these are crashes with huge amplitude. US markets go down more than 20% in a single day. This is, if markets, as I'm going to explain, were reflecting something real, it would mean that somehow, suddenly, the economy loses 20% of its value. But it's not the case. It's a kind of anecdotal trigger that leads to crashes of that amplitude. There are other crashes, many of them, most of them you haven't heard of, and actually it's a little bit like earthquakes. There are big earthquakes that make the news, and little earthquakes that happen all the time that we don't even speak about, or that we don't even feel, actually. It's a little bit the same in financial markets. So let me quote two of them that are interesting. Maybe some of you have heard about them. One is 6th of May 2010. 6th of May 2010, the US market goes down by like something 10% in a few minutes, like 10 minutes, and then rebounds and ends the day at minus 3%. And no reason, again. So people have pointed fingers at high-frequency finance, which was a topic at the time. Now we understand it's not really a problem. But what is interesting is that in 1962, 28th of May 1962, which happens to be my birth year, the same happens. In the US market, the market goes down 9% in 10 minutes and then rebounds. And of course, there's no high-frequency trader there. So what all this means, and of course, if I had time, I would show you a lot more data to substantiate my claim, is that financial markets appear to be intrinsically unstable. And they only partly reflect some underlying economic reality. So it might be, it might sound obvious to many of you, because the layman thinks that there are bubbles and there are crashes, and maybe all this is not real. But as I'm going to say, economists think completely differently, and that is the whole point of my lecture tonight. What is interesting is that this propensity of systems like financial markets to self-excite, to be prone to endogenous agitation, is not restricted to financial markets. It's true for more global economies. And that's the graph on the top right, this is the yearly growth of the US GDP from 1950 to nowadays. And what you can't really see is that the average of this is around 3%. So the economy grows since the 50s around 3%. But it's 3% plus or minus 3%. There are years where it's 6%, there are years where it's minus 3%. It fluctuates a lot. And this is a problem, as I'm going to say, for economic theory. The large economy like the US shouldn't fluctuate for no reason at all. Of course, there's COVID. Of course, there can be the oil shock in '73. There are clearly exogenous reasons for the economy to move around, but many of these fluctuations cannot be explained by something plausible. So what I said about financial markets is actually true also for the real economy, if you want. So the whole economy seems to be prone to endogenous agitation. And as I said, this is a problem for economic theory, because the standard economic theory posits that economic agents, firms, households, are rational, and therefore financial markets should be efficient, what's called efficient, which means that prices should always reflect fundamental value, should always be very close to fundamental value. So if markets go down by 20%, it is because fundamental value goes down by 20%. And economies should settle in a unique optimal equilibrium. On top of that, it's optimal. And it's this equilibrium that's buffeted by exogenous shocks, like technology shocks or disasters, earthquake in Tokyo or COVID. So if you want, the picture is a little bit what I've drawn on the top of my slide. So you should picture the economy as a marble in a ball. So if you don't move the ball around, the marble will fall at the bottom of the ball and nothing should happen. It's only because an exogenous force shakes the ball around that the marble has fluctuations. Otherwise, nothing would happen. So there's nothing endogenous that is possible in classical theory. It's also this horse that could be a picture of what happens. If you leave the horse alone, it's going to be stable. So then 2008 hit, the big crisis in 2008 that most of you may remember. And here I want to quote several economists, their reaction to what happened and to the way we should understand what happened. So for example, Eugene Fama, who's the Nobel Prize 2013, said in 2010, just a few years after the 2008 crisis, he was reflecting on what happened, and he said prices, financial prices, started to decline in advance of when people recognized it was a recession. That's exactly what you would expect if markets were efficient. So you see, he goes very far in the dogma, because he says markets crashed because they anticipated there would be a recession. Whereas I think most of us would believe it's the other way around, that there was a problem in the financial sector that then channeled into the rest of the economy. So you see, it's a state of mind, it's a way of thinking about the world that's completely different and has policy implications, of course, and that's the point of what I want to speak about also. Another Nobel Prize in economics, Bob Lucas, in 2009, just after the crisis, said the 2008 crisis was not predicted because economic theory predicts that such events cannot be predicted. End of story. Which I find particularly shocking myself, but I leave you to judge. Maybe, just maybe, economic theory fails to capture some crucial features. And so, we shouldn't take that for granted. We should dig further. Another interesting quote, I think, is that of Jean-Claude Trichet in 2010. So it was in Frankfurt at the ECB, and I was fortunate to attend that particular conference. And he said, he was expressing his dismay when the crisis hit. He said, the models used by central bankers, based on these assumptions that I described to you, models failed to predict the crisis and seemed incapable of explaining what was happening. In the face of the crisis, we felt abandoned by conventional tools. A little later, in 2014, Olivier Blanchard, who was head economist at the IMF, wrote a paper that I really recommend if you're interested in these matters, which is called Where Danger Lurks, and it's easily available on the web. And he says, we in the field did think of the economy as roughly linear, constantly subject to different shocks, constantly fluctuating, but naturally returning to equilibrium over time. So this is really my marble in a ball. The main lesson of the crisis, he means the 2008 crisis, is that we were much closer to dark corners, situations in which the economy could badly malfunction than we thought. And what I want to try to convince you of is that maybe we can give a precise meaning to these dark corners as events that can be understood as collective phenomena that statistical physics is trained, in a sense, to describe. So let me go back a little bit to the standard theory before trying to introduce concepts that I feel are missing. So as I said, classical economic equilibrium is usually expressed in terms of a rational representative agent. So representative agent means that instead of describing every one of you in this auditorium, every one of us in a society, we're replacing everybody by a unique guy who's supposed to represent everybody. And on top of that, this guy is supposed to be extremely smart. He's supposed to be rational. He's supposed to, or she is supposed to optimize her present and future interests. And there are also rational firms who maximize their profits and are able to produce just enough such that markets clear, as economists say. That is, demand equals supply all the time. So if you assume all this, as I said, prices and production only fluctuate because of exogenous shocks. They can't have a kind of spontaneous dynamics that would lead to unwanted crisis. But if we reflect a little bit, if we self-introspect, as maybe Freud started doing when he invented psychoanalysis, I think we all have to agree that we're very far from this rational homo economicus that is posited by these theories. First of all, we are very strongly heterogeneous. We're heterogeneous in wealth, in beliefs. Political debate is something that never stops, so it means that we have fundamentally different views about the world. And it's strange that we can't agree on things. It seems that there are deeply embedded ideas that we can't agree on. We are also subject to the same cognitive biases. And here I want to show you something that maybe some of you already know, which is a well-known optical illusion. But it's so strong, this illusion, that even when you know about it, you can't make your brain correct it. So the idea here is that there's a checkerboard here with two squares that are labeled A and B. And there's this cylinder here that makes a fake shadow on the plate. And so all of you, I guess, will see that A is darker than B. B looks like white, and A looks like dark gray. But actually, I've actually copied and pasted myself the two squares here and glued them together. They're exactly the same color. But the illusion is such that it is playing on the fact that your brain is so much trained to interpret what you're seeing as a chessboard which alternates dark and white, and also the illusion made by the shadow here makes your eye or your brain interpret what it sees as one square darker than the other. And what I find striking is that I tell you that, and I know that, and you're unable to correct for it. And we all have the same biases. And so it means that biases, they don't average out when you take a large population. Sometimes the economists say, okay, we are not rational, we have biases, but if we take large populations, maybe these biases, maybe these errors cancel out. Some think that, for example, in financial markets, the price should be higher, other things that the price should be lower, and on average, it works out. We're also in a hyper-complex, non-stationary world. I mean, it's hard to believe that we can, of course, the past is always a good, it's good to know history, and it's always good to know what happened in the past, but it's impossible to really think that the world is repeating itself, even in a statistical manner. There are true innovations, true surprises that make the theory of the world a very complex object. So, you know, the idea of rationality in a world that's super complex is a problem. But most of all, and that's what I want to spend the rest of the presentation on, we're extremely strongly interacting with one another. We're influenced by what other people do and think, and I'll show various examples. And this is also a very big concern for classical economic theories, because some unexpected collective effects can appear because of these interactions. Complexity can appear because people interact, because objects interact. And maybe the dark corners that Olivier Blanchard was referring to are these emerging collective effects. So here I want to quote a giant of the 20th century, Phil Anderson, who passed away a year ago, or maybe 18 months ago. Nobel Prize in Physics, could have had two, I guess. And he wrote a fantastic paper in Science 1972 that is already quite well known, the title of which is More is Different. And I've emphasized different because, you know, he doesn't say that the whole is larger than the sum of its parts, which is the standard thing that people say. He says the whole is different from its parts. Not more, not less, but different. And he says the behavior of large assemblies of interacting individuals, so actually it's a physics paper, so he says particles, but I want to already translate it to individuals, cannot be understood as a simple extrapolation of the properties of isolated individuals. Instead, entirely new, unanticipated behaviors may appear, and their understanding requires new ideas and methods. And so as an illustration, I'm showing photos that may be anecdotal at this stage, but I think they are extremely interesting. One is starlings in the sky of Rome. So all these little birds managed collectively to create a superbird that supposedly is there to scare off predators. But you see this emerging behavior that's really spectacular. And by the way, Giorgio Parisi, who, as you know, had the Nobel Prize last year, was part of the group studying these collective effects in bird flocks. This is not a very spectacular photo because it should be a movie, actually. These are fireflies flashing in unison, and I'll go back to that in a second. And this is, of course, a little cartoon making little fishes look like a big fish and scaring away the big fish. So it's here to illustrate the fact that collective effects can be surprising. So let me speak about fireflies for a second, because the fireflies in disguise will appear later in macroeconomic modeling. So this is from Steve Strogat's book called The Emerging Science of Spontaneous Order. And the introduction of the book tells the story of these fireflies. And he says, for 300 years, Western travelers to Southeast Asia had been returning with tales of enormous congregations of fireflies blinking on and off in unison in displays that stretched for miles along the riverbanks. So I guess you can all imagine how it must look like to have miles of fireflies flashing in unison. I wish I can see that before I die. How could thousands of fireflies orchestrate their flashing so precisely and on such vast scales? For decades, no one could come up with a plausible theory. Actually, some people said it was a mere illusion. It was just our eyes opening and closing and giving us the impression of these flashing. A few believe there must be a maestro, which indeed is a kind of natural hypothesis. If these fireflies are able to synchronize, it's because there's a maestro. a fireflies that cues all the rest. Only by the late 60s did the pieces of the puzzle begin to fall into place. And so the whole book is about the story. And essentially, it's because people started thinking about neurons and the way neurons in our brains synchronize to realize the task that they're supposed to realize, that people realized that we had to come up with a scientific theory for this synchronization. So statistical physics is the science of collective effects. It was actually, partly created to understand this phenomenon that we're so used to that we don't even that we forget it's somehow miraculous. And the phenomenon I'm referring to is, the one we have daily experience with, which is the fact that water at 0 minus and 0 plus behave completely differently. But it's the very same H2O molecules. The H2O molecules haven't changed. They haven't changed shape, they haven't changed size. It's the same. So how is it that the very same molecules on aggregate can behave so differently? At 0 minus, they are behaving like a solid, white. At 0 plus, it's a liquid that's blue. How is it possible that the same microscopic objects behave so differently at the macro scale? And related to this observation, there's this well-known phase diagram, which I think is a very important concept, which is, again, something that probably all of you remember from high school. And what I'm going to insist on for a second now is the fact that although all the simple bodies are different, water is not the same as glycerol and not the same as ammonia or any other substance, but most simple bodies have exactly the same phase diagram in terms of its topology. There's always a solid phase, a liquid phase, and a gas phase. And within each of these phases, nothing much happens. A solid at ice at -10 and ice at -20, they're a little different, but essentially it's the same thing. It's a rigid body. Same in the liquid phase. So there are quantitative differences, but not qualitative differences. The qualitative differences are localized on these boundaries. They are localized on phase transitions. And so what's amazing, I think, and what statistical physics really taught us to understand is that very different objects at the micro level can behave very differently at the macro level. And at the macro level, something very simple appears, a phase diagram with only 3 possibilities. But we know that there are other types of surprises that can happen at the macro level. So this idea that surprising collective effects stemming from interacting but banal elementary units is also at play for superconductivity, for example, or superfluidity. You know that at low temperature, metals can conduct electricity without friction, without dissipation. Electrons as a whole manage to percolate through the solid without losing energy. And this is a collective effect. I spoke about neurons. Our brains is made of millions of neurons. And of course, everything that makes us humans conscious is a collective effect. It's the way the neurons interact with one another that makes memory possible, or consciousness. Of course, consciousness doesn't belong to a single neuron. Memory doesn't belong to a single neuron. It's something different at the macro level. I spoke about bird flocks, fireflies. You can think about Mexican waves in stadium, which is an interesting collective effect also. But maybe more seriously, panics, opinion shifts, crisis, all these things may be related to this very strong interaction between individuals. And at this stage, I just want to remark that these arguments that I've said about the difference between micro and macro means that you can very well think of agents that are rational at the micro level. We could all be extremely rational like economists think we are, but because of interactions, we could collectively behave as an irrational crowd. And vice versa, we could be irrational, and behave as a rational crowd at the aggregate level. And this is the leap of faith that is made by standard economic theory. As I mentioned earlier, if we believe that our biases and our errors kind of average out because we're not interacting, then maybe we can believe the rational representative agent story. But if we start interacting and if our biases don't cancel out, something completely different can appear. So let me be a little more specific about this. So let's look at these fishes swimming as a school fish. And each of these fish has probably no idea where it's going. So if he could speak, or she could speak, it would say, I have no clue where I'm going, so I follow my neighbor who orients itself with respect to its own neighbor, but that includes myself. And so you see that there can be a feedback loop which makes the collective motion of this school of fish coherent, flowing in one direction, but maybe this direction is chosen completely randomly because there was no reason for this school of fish to choose one particular direction rather than another. So there's a lot of ways humans and animals interact. Fishes and birds interact through vision. We know that some animals interact through smell. I think humans, we mostly interact through speech or writing. If you imagine the number of hours that we spend speaking to each other, it can't have zero impact on the way we behave collectively. I think that it's striking to think that one of the main human activity is to communicate. Maybe trivias, maybe important information we don't know, but at the end of the interaction between humans, there are narratives that come out and that seem to be focus points of societies. At one moment in time, everybody seems to focus on very few subjects, and these very few subjects influence the behavior of people. So in physics, we know that when interactions are weak, so here I represent the standard model for collective phenomena in solid-state physics, which are magnets. So in a magnet, these little spins here, these little arrows interact with one another and tend to polarize their neighbor in the same direction, much like my fishes here tend to influence their neighbors to fly or swim in the same direction. And so what we know from physics is that when the interactions are weak enough, then nothing particular happens at the macro scale. The arrows are completely random, or the fishes would swim in random directions. Nothing consistent, coherent would happen. But if interactions are strong enough, then these collective effects start playing a role. And as I've mentioned, these phase diagrams show that there are usually special points which separate two very, very different types of behavior. And we are social animals. Here I'm quoting Henri Poincaré, so maybe you allow me to read it in French. Quand des hommes sont rapprochés, ils ne décident plus au hasard et indépendamment les uns des autres, ils réagissent les uns sur les autres. Des causes multiples entrent en action, elles troublent les hommes, les entraînent à droite et à gauche, mais il y a une chose qu'elles ne peuvent détruire, ce sont leurs habitudes de moutons de panurge. Here are a few anecdotal or more serious examples. These are lovelocks on Pont des Arts. Pont des Arts was a bridge I was fortunate to cross to walk to work every day. And it was absolutely amazing. In a matter of a month, the Pont des Arts had a few of these lovelocks. And after a month, it was completely full of these lovelocks. Like there's an urge of people to do what other people do that is kind of uncontrollable. And so it's maybe not a very deep example, but it's a striking one. Another anecdotal maybe example is how people name their children. So as maybe some of you remember, in 1965, this little girl, Stéphanie de Monaco, came to life. And after that, there's this incredible peak of the number of Stéphanie born in France, reaching the amazing number of 23,522 in 1973. Like, you know, people, again, couldn't resist naming after their friends. Or this is a much more serious effect, which is a bank run. Bank runs are when people fear that they won't be able to cash their money at the bank, so everybody wants to be first to cash their money because they fear that if they're not the first, there won't be enough money. And of course, this creates the problem, because banks, as you know, never have enough money at one instant of time to give back to all their clients. This is what happened in 2008. So in 2008, there was the start of the crisis that I mentioned earlier, and there's a gauge, an indicator, which is the red line here, which I won't try to explain in details. It's essentially a measure of how banks trust or distrust each other. As you may know, banks, there's the interbank lending market. Banks have to adjust every night their positions, so they need always to compensate and loan from other banks or lend to other banks. And so there's an interest rate associated to these very short loans. And this is the red line. And so when the interest rate goes up, it means that nobody wants to trust anybody anymore. And what you see is that in October 2008, just after Lehman's default, there was a huge spike in this interbank loan rate, which amounts to collective loss of confidence. And if you try to think of what happened, you know, again, nothing material happened in 2008. It's really something like I've panicked because you've panicked because I've panicked. And this loop creates something that's visible here on the graph. And by the way, I'm not the only one to think that this happened. Ben Bernanke, who was the chief of the Fed at the time, wrote a fantastic book, which again I recommend to all of you, called Firefighting, or The Firefighters, I don't remember, where he recounts the events of 2008 and he insists on this collective loss of confidence. This is another example of how bad loss of confidence can be and how it can affect everybody's life. So I guess that we're all convinced of that, but in the days of increasing inflation, I'm showing you a real banknote here. The Reserve Bank of Zimbabwe printed a $100 trillion note. And it's approximately the same order of magnitude as the depreciation of the mark in the great hyperinflation in the 20s. So these collective loss of confidence on the value of money, they can have real consequences. So how can we try to anticipate these collective events, these events that defy intuition, that defy imagination? Here I want to quote a scientific journalist called Mark Buchanan, who wrote in the New York Times just after the crisis again, an opinion piece called This Economy Does Not Compute, which is again something that you can find easily. And he says various interesting things, but he says something that I think physicists are very convinced of, but he says it very eloquently, and I find his analogy extremely deep. So he says, done properly, computer simulation represents a kind of telescope for the mind, multiplying human powers of analysis and insight just as a telescope does our powers of vision. So that's why I represented Galileo here, looking at the sky through his telescope. And of course, with a telescope, you can see things that your bare eye cannot see. And computer simulation brings to your intuition things that you might not have thought about. With simulations, we can discover relationships that the unaided human mind, or even the human mind aided with the best mathematical analysis, would never grasp. And of course, this is now standard. Speaking about events that nobody predicted goes under the name of black swans. So as you know, black swans were not observed before Australia was discovered. And so people didn't believe that, people believed that swans were all white. And this is a kind of paradigm to explain that some of the events are just unthinkable. But the point is that a lot of the events that people name black swans are only black swans because of our lack of imagination. So I think the idea of numerical simulation, the idea of trying to have a peep under the curtain using numerical simulation to anticipate these surprises is a way to reduce the realm of these black swans, to actually realize that many of these black swans, we could have anticipated them. And in particular, the 2008 crisis, I think, was very, very far from a black swan. So again, numerical simulation is something that is already now extremely well used and recognized in various fields, in physics, in engineering, in epidemiology, social sciences. It's starting to be recognized in economics as well. Not enough, in my opinion. That's going to be what I will finish on. And numerical simulation means that you're really looking at things at the individual level, taking into account heterogeneities, which I've said are important, interactions, maybe biases. These are very difficult features to include in a complete analytical theory, but they're very easy to implement in a numerical simulation. And a numerical simulation allows you to do experiments with computers. So they allow you to create worlds and to see what happens if you give your world some rules. So you, in a sense, you play God when you do a numerical simulation. You invent a world where agents do this and do that. And what is interesting, of course, is to see what happens at the global level, at the collective level. What are the surprises that emerge from this soup of banal and uninteresting individuals? So the rule of these simulations is that each agent particle follows simple rules, but at the macro level, you have something unexpected appearing. And here, what I want to illustrate is something that is already an interesting surprise, is how silos empty. So this is a model of a grain silo. And what happens if you try to empty a grain silo with no special feature around the little opening here, is that these grains will jam, will create kind of arches and block completely the exit. So after a while, because of this jamming, nothing will come out. So a way out that was understood by engineers and that you can reproduce by these numerical simulation is to put actually an obstacle in front of the door, in front of the exit. So this looks completely paradoxical because you're actually seemingly reducing the possibility of these grains to go out. But doing so, you're organizing the flow in such a way that actually grains flow faster than without this opening. And by the way, this method was implemented in Mecca to avoid crowd stampedes when huge crowds try to exit the big square in Mecca. So there's now a huge column that makes this engineering of the flow. So there's more and more data. We're living in a world where there's more and more data about everything, about what people do, how they consume, how they behave, how they wake up in the morning, they go to work. With our little cell phones, we're tracked. We can be, at least statistically, everything is known. So you can have information on agents in the metro station. You can have information about the fly routes in the air industry, and use these inputs to model virus propagation and so on. So we're heading to a situation where there's going to be more and more data to know what people do at the individual level, and therefore we can think that we're going to be able to simulate large societies and see what happens at the macro level and anticipate these strange collective behavior. So let me quote one, which is, if you want, the first simulation, the first what people call agent-based model, agent-based because it's based on individual agents. And this model was invented by Thomas Schelling, who's another Nobel Prize in Economy, by the way. And this is a model that dates back from 1970. I think it's a beautiful model because it illustrates a situation where the proverbial Adam Smith invisible hand badly fails. So probably you all know about Adam Smith's invisible hand, which is supposed to say that it is because of the selfishness of the baker that we eat our bread every day. So it means that if everybody is acting selfishly, then the society as a whole can behave optimally. So what is this model? So Schelling was thinking about racial segregation in US cities. So here, the version I'm going to give you strips away the racial or social aspect and is going to focus on the crowdedness of the neighborhood people want to work in or live in. So this version was actually proposed by 4 physicists here, Grovin, Bertin, Lemoy, and Jensen, and they showed that the mathematics of the model I'm going to describe is equivalent to the liquid-gas transition that I've already mentioned. So this idea of phase diagram is pervasive. So what are the rules of the game here? What are the rules that Schelling proposed? Well, he says people live in different neighborhoods that are represented here as little squares in the big square that's the city, and people tend to prefer living in half-filled neighborhoods. You don't want to live in an overcrowded neighborhood because it's difficult to park, it's noisy, and so on. You don't want to live in an empty neighborhood either because there's no bar and blah, blah. So let's assume that everybody prefers to live in an exactly half-filled neighborhood. So the little graph here that is shown, oh, you see my hand, so that's good. So this is the density of the neighborhood. 0 is empty, 1 is completely full. And the maximum of the so-called utility function, the satisfaction of agents, if you want, is maximum for a density which is 1/2, which means half filled. And so you would believe spontaneously that if everybody wants to live in a half-filled neighborhood, and if there's enough space to accommodate everybody, then the resulting configuration should be that one, where indeed everybody lives in half-filled neighborhoods. But actually, if you iterate a rule, which is Schelling's rule, which is that people can move and go to a neighborhood that's closer to 1/2 than the neighborhood they're presently living in, lo and behold, what happens is a completely opposite outcome, where some neighborhoods turn out to be completely empty, and other ones, well, not completely full, but much more filled than 1/2. So agents segregate against their own will. They would like to be in half-filled neighborhood. Everything conspires to make that possible, but because they act in a selfish way, and technically it means they don't take into account the pain they inflict on others when they change neighborhood, because when you change neighborhood, you change the density of the neighbor that you're leaving. So people are left off being less happy. Then, if you don't take into account what happens to your neighbors, if you want, the outcome turns out to be completely different from what you would have expected. So I think Schelling was a hero in his kind, and he was very close to statistical physics in a sense. But I think this is a very good illustration of the type of surprises that you can encounter in these situations. I have completely lost track of time, so someone has to tell me how long I can speak, otherwise I'll be here for the whole evening. Okay. So, what we try to do with 3 colleagues, Francesco Zamponi is at Ecole Normale, and Marco Tarzia is in Jussieu, both statistical physicists, and Stanislao Gualdi is actually now working for CFM. We try to come up with a macroeconomic agent-based model of the kind that I've discussed, where we are trying to describe everybody and see how the emerging behavior what kind of emerging behavior one finds. And so we wanted to illustrate this idea of phase diagrams and surprises in the context of macroeconomic modeling. And the objective here is to try, the final aim is to try to replace the models that central banks are using, these models that Jean-Claude Trichet was complaining about, because these models never predict anything endogenous. They never predict crises that can happen out of the blue. We would like, at the end of this long process, I'm sure, to be able to do better. So we tried with a very simple setting. So let me explain in a few words what our agents are doing, and just trying to convince you that all the rules that we're trying to implement are very intuitive in a sense. So in our agent-based models, there are firms and households. There's also a central bank, but I won't speak about this. And firms, they have to produce something, they have to set wages, and they have to hire and fire the workforce. And our firms, they're heuristic. They're using heuristic rules. They're not trying to do these complicated optimization calculation that I feel nobody's able to do. And as Edouard mentioned, I'm co-running a company now with 4 other board members, by the way, so I'm sharing the load. And I can tell you that it's clear that we're not doing very complicated calculations to decide what we want to do. We're using heuristic rules. So our firms in this model, they're using these heuristic rules. So what does it mean? It means that if they see that production was too high compared to consumption, well, they're going to try to reduce production, so they're going to lay off some people, and they're going to try to reduce a little bit the prices at which they sell their products. And vice versa. If they underproduced, they're going to hire more and or increase their prices in the next time round. So there are parameters describing this behavior, but there's one parameter that turns out to be very important in the behavior of the model, and this is the speed at which firms hire or fire. So if you want, the idea here is that if labor laws make it difficult to fire people, then reaction when they need to hire will be faster than when they need to fire. And in this case, this ratio will be greater than 1. If, on the other hand, firms fire faster than they hire, this ratio will be less than 1. So we have households. Households, they have a consumption budget, okay, and they favor firms with low prices, which is, again, very intuitive. And then our firms, because there's uncertainty, they can't always make money. And actually, sometimes they make money, sometimes they lose money, like in the real world. And so some firms do well, but some firms accumulate debt because they've been losing money for several years, several rounds. And we accept that in the model. We accept that firms can go into debt, but we say if the debt accumulated exceeds a certain multiple M of the total sales, then the banks will stop lending to these firms and declare them bankrupt. So if you want, this is again trying to model something that happens in real life. Firms go into debt, but if the level of debt becomes too high, then they are forced into bankruptcy. But because we want our economy to be, not deprived of firms at the end of the game, when a firm defaults, with some probability a new firm comes in the game and replaces a defunct firm. So we have a constant number of firms on average. And that's about it. So that's what you need to know about our game. So we invented an economy, if you want, which is based on simple rules, simple, plausible rules. And what we want to know is the miracle of statistical physics taking place? Is it true that in these kind of models, independently of the details of the rules, of the details of the parameters, a kind of robust phase diagram, like the liquid, gas, solid that I've shown before, is it the case that it's also true in a model that's completely different from molecules interacting in physics, right? We have a completely different setting. And what is nice is that exactly the same thing happens. There is a phase diagram emerging, which is extremely robust. Like this solid liquid phase gas phase diagram, it doesn't depend much what kind of precise assumption you make on the behavioral rules of our firms and households. What emerges is something that is always the same thing. And what emerges in our case are four possibilities. One, which is that the economy completely collapses. This is the black phase. So if you remember, M is the amount of debt that you can accumulate, and R is the ratio of hiring to firing. So what it means is in our model, if there are no labor laws, the economy collapses. Of course, it's a proof of concept model. I'm not saying this represents the world. It's a proof of concept in the sense we want to see whether this idea that what emerges at the macro level is extremely robust about the micro rules also takes place in these kinds of models. So there's a collapse phase, there's a full employment phase, where firms are allowed to go quite deep into debt, but they recover, and so this allows unemployment to go to zero. But what is completely surprising, and that's the whole message I want to convey tonight, is that we found this strange phase here, which we call endogenous crisis. And what is endogenous crisis means is that if you look at the unemployment as a function of time, it's very low, and then from time to time, out of the blue, for no reason at all, there's a crisis. The unemployment goes up very quickly, and then the economy recovers. And this was so surprising to us that we thought there was a bug in the code. So we worked very hard to understand that this is real. This is real and is related to a feedback loop that is in our model, and I guess you'll agree that this is a feedback loop that can happen in real as well. But surprisingly, this feedback loop is absent in the economic models that I've alluded to. So what is this feedback loop? Well, a firm defaults means that some people are unemployed. So it means that there's less consumption, there's less budget to consume. So other firms will suffer from that. And so you expect more defaults. What is absolutely non-trivial is that these defaults can synchronize and cluster and lead to a crisis. Instead of having these defaults happening at random in time, because of interaction, they can coalesce and lead to these very strong spikes that I showed before. So why is that interesting? Well, first of all, because I'm not going to go into the equation, but we were able to make a model of our model and understand that this is real and do the mathematics to show that indeed you find that these oscillating peaks can happen in such a model. But what's interesting is that it's the same scenario as for fireflies that I talked about earlier. The mechanism by which fireflies are able to synchronize and the mechanism by which defaults in our economy can synchronize is interestingly the same. So I'm going to wrap up quickly. As I said, this is a very simple model that was just there to illustrate the miracle of statistical mechanics, if you want, the emergence phenomena. But when COVID hit in 2020, it was too tempting. So with the same authors and a PhD student, Dhruv Sharma, we adapted our model to try to guess the shape of the recovery post-COVID. Maybe you remember that in the month between March and June 2020, people were asking what's going to happen. Is the economy going to recover? Are we going to be in a long, drawn-out recession, and so on? So we played with our model, and we were able to find different outcomes. Some crises led to V-shaped, so output goes down. So this graph shows output as a function of time. So you have a V shape where the output goes down and then recovers quickly. But you can also have within the same model what people call L shape, which is no recovery at all. So what happens in our model? Well, what happens in our model is again the same story of phase transitions. Again, the same story of the possibility of having solid or liquid. So this graph here is again a phase diagram, and the x and the y-axis represent the amplitude of the shock of the COVID crisis. So maybe you remember that people spoke about the crisis induced by COVID as a special one, because it's a crisis both in terms of demand and supply. During the crisis, during the lockdown, people couldn't go to work, so supply went down, but also couldn't consume, so demand went down as well. So this is the demand shock on the x-axis, and this is the supply shock on the y-axis. It's not very important. What is important is that if the shock is sufficiently mild, we get a V-shaped recovery. But if the shock is sufficiently strong, we go to this other phase, which is L-shaped. And the point here is that agent-based models are much richer in the kind of behavior that you can get. If I compare these predictions with the models that are called the SGE models, dynamic stochastic general equilibrium is the word describing standard economic models, then in the models that Trichet complained about, the only thing you can get is that recovery is complete. Because remember the marble in a bowl, if you stop shaking the bowl, the marble will go down. So it means the economy will recover. So then these are two different studies using these CSG models. You see that the recovery can have different shapes, different durations, but at the end, output reaches its pre-crisis level. Whereas in our model, it's not the case. And so we tried to play a little bit with our model, and we said, okay, let's do policy experiments. This is the great thing about these agent-based models is, as I mentioned, you can do numerical simulations, you can do experiments that you couldn't do in reality. And so doing these policy experiments, we've shown that it was possible actually to avoid an L-shaped recovery. So that's what I'm showing here, with no policy allowing firms to survive even if they get indebted, you get an L shape, but allowing firms to get over-indebted, so changing the policy if you want, you're able to get back to the V shape. And what we found at the time, and we said, okay, this is interesting, is that after the recovery, there's more inflation. So of course, we know that this is what is happening now, and I won't boast that we predicted it. This is not true. But what I found very interesting at the time is that it was an experiment that was showing that in some cases, saving the economy would go hand in hand with higher inflation in the future. So the main message of these models is that classical models that have a unique equilibrium, they tend to overestimate the resilience of the system, and they tend to disallow the existence of these endogenous crises that I talked about since the beginning. So let me finish by a conclusion. So the title of this conclusion slide is Complexity, Prediction, and Humility. So in science, we're often led to believe that a good science is a predictive science in the sense that we should be able to predict hard numbers. We should be able to predict, I don't know, the G-2 of the electron or things that can be measured and very precisely. But in very complex situations, maybe prediction needs to have another meaning. Maybe we should, instead of thinking that we need to predict numbers, we need to predict scenarios. We need to get the full scale of possibilities qualitatively first. Maybe, if we're lucky, we'll be able to hone in and get more precise numbers. But the first task, I think, in a complex situation, and I guess that everybody in this audience will agree that the economy is extremely complex, so we should maybe be more humble and start thinking about how to not be surprised by scenarios that happen. So simulation and scenarios, in my view, is the future of complexity economics. Agent-based models are great tools to imagine scenarios that are very hard to imagine otherwise. So this is the telescope for the mind that I talked about. Collective behavior, tipping point, endogenous crisis are things that happen, I believe, in reality, and they need to be accounted for by economic models. Physics is well trained to do this, and I think that including these ideas into economic models will be very interesting for the future. And here I want to conclude with two quotes by another of my heroes, Keynes, who in the 30s seemingly understood all this. So he said, "We are faced with the problems of organic unity," by which he meant collective effects, "of discontinuity. The whole is not equal to the sum of the parts. Small changes produce large effects." So you can see that everything in this sentence is what I talked about today, and this was written close to a century ago. But he also said something that is very relevant to my conclusion, and I feel it's extremely true for economics. It is better to be roughly right than precisely wrong, by which he means that, you know, if you're very precise but off the mark, it's probably not as good as being roughly around the target. And on this note, I end, and I thank you for your attention. Est-ce qu'il y a un micro?
So we can take questions.
Yeah, I have a question about behavioral assumptions on behaviors. I mean, how do you validate the assumptions which are critical in order to build models? So how do you...
Yes, thank you.
Yeah, you make a dialogue with scientists from social sciences. And
I think it's an extremely good question. First of all, we have more and more data about actual behavior of people. So I think that they will be, you know, they can be included in models down the line. But what I try to insist on, and I think this is really my motto in a way, is the fact that you have to come up with predictions that are not too critically sensitive to parameters or to assumptions. And maybe I didn't convey this clearly enough. This was really the aim of this work that I'm showing here. It was to show that whatever you do at the behavioral level for individuals, provided it's not silly. I mean, you know, of course, this is robust if you have firms that act in a way that you would qualify as reasonable. If firms start to increase their price when they're underselling, then everything that I've talked about might completely disappear. But provided firms and households behave, you know, kind of reasonably, doesn't mean rationally, but in a satisficing way, as Herb Simon would say, then the same emerging properties happen. And I think this is the deep lesson of, that's why I try to insist on this idea of phase diagrams. This is the deep lesson of statistical physics, is that it doesn't matter whether you're describing water or glycerol, you'll have the same emerging properties at the macro scale. Of course, the parameters will change. So, of course, as we all know, water is freezing at 0 degrees Celsius at normal atmospheres, and other bodies will freeze at a different temperature. So the precise location might not be the same, but the phenomena is the same. And I think that before trying to pin down numbers, again, you know, that's what Keynes said, we should first understand the emergent behavior. We should first understand the scenarios. So we should scan the space of parameters, if you want, the space of of assumptions to see what happens. And if something happens that is unexpected, you should say, so if I assume that people are actually doing this, that can happen. Well, I hadn't thought about this, and maybe I should take this into account in the way I design a policy. I mean, the whole thing is about unintended consequences, if you want. But I agree that, and that's what I said at the end, it's a humble aim, in a way. You know, I'm saying maybe we shouldn't try to be too precise in a first go. We should maybe just restrict to a more humble aim, target, which is to understand the possible scenarios. And I think if we are able to do that, I think we're already quite far in improving the current state of the art. But there's, of course, a lot to do. I mean, I didn't insist on that, but my subtitle was Economic Crisis, a Physicist and Perspective Point of View. I think there's a lot to be done in these directions before proposing them as a new alternative.
So if I may add just a follow-up, so thank you very much. It was very interesting. I'm just wondering, how do you choose in these micro agent-based models your collective variables? I mean, you present this R. As you mentioned, you could have chosen other variables.
Okay, so that's a very interesting question. It may be a little technical. So we tried first to, so there are quite a lot of agent-based models, macro agent-based models that have been proposed, but unfortunately they tend to have so many parameters that it's impossible to even understand what's going on. So what we try to do is, first of all, to have a baseline agent-based model that only has 7 parameters, which is a lot, but not that much. And so we've been able to kind of, by hand, navigate in this phase space and identify the crucial parameters, which turn out in this case to be R and M, and that's the ones I've shown. But it so happens that there are new ideas that allow you to devise an algorithm that navigates in a systematic way in a large dimensional space and allows to reduce the dimensionality of the problem in a systematic way. And so we've applied that more recently to the same model, and this is, I think, very, very promising. And this is called sloppy models. If you're interested in the physicist who wrote a lot about this is Jim Sethna, S-E-T-H-N-A. I think it has a lot of promises, because of course you're right. This is a main problem. The fact that you're lost in a high-dimensional space. Yes?
Professor Bouchaud, I have enjoyed your lecture very much, but I have noted that you have avoided the word mathematical throughout your lecture. And we have mathematical models and statistical models. I have worked all my life on mathematical economic models. And I will give you an example. For example, the pendulum is the most elementary mathematical model in physics. We all know what's the pendulum. We can have a precise model of the pendulum. I was wondering how we can have a statistical model of the pendulum. I've never seen one, and I do not understand how it can be done. So I would like you to say a few things about differences between mathematical models and statistical models, if possible.
Well, I'm not 100% sure I understand your question, but you know, underlying all this, there's a lot of mathematics, of course. I tried to remove the mathematics, but for example, here, there's a clear mathematical modelization of what happens that we can deal with. But I'm not sure that was your question. But anyway, I didn't speak about mathematics because I don't think it's the venue to speak about mathematics. You know, if you speak about deterministic model versus statistical models, then I think this is, again, the whole story.
It's quite near the terminology deterministic and statistical, is quite near what I mean, yes.
Yes. Well, this is, again, the whole raison d'être of statistical mechanics, in a sense, is to replace deterministic laws of motions of the pendulum or of collisions between atoms by a statistical description, because we know that most of these motions are actually chaotic and unpredictable. So if you want to add noise on a pendulum, this is also the simplest model of statistical mechanics. It's a pendulum with temperature, with fluctuations, and we know everything about it as well. But what is interesting in this context is that there's a notion that goes from classical mechanics to statistical physics, which is to recognize that most systems are chaotic, are not describable by a simple pendulum dynamics. But what's interesting about complex systems is that you have to go one step further, because in simple chaotic systems you can replace deterministic trajectories by a probability distribution, which is Boltzmann distribution or the ergodic measure or whatever you want to call it. But in chaotic systems, and this was again one of the great insights of Giorgio Parisi, is that the notion of probability itself becomes chaotic. So depending on the parameters of your model, the distribution, the probability distribution that describes your model is going to change chaotically from one set of parameters to the next. So I think that we're beyond this distinction between deterministic and chaos. We're at the level of having systems that are a degree more complex to describe.
Thank you, Professor.
Thank you very much for sheer delight, really so much to comprehend and appreciate. I'll come back to a question I had actually, but my colleague asked a similar question. In a way, we understand the collective parameters, inflation, growth, the ones that the economists use. And if we bring this to physics, as you clearly indicated, would be pressure, temperature, the macroscopic variables that, let's say, thermodynamics has invented. In this case, how do you choose and which are the microscopic degrees of freedom and parameters out of which you'll construct the macroscopic parameters?
So there are two different things, right? There's the microscopic parameters and the macroscopic variables, the macroscopic emerging observables. So one is a set of parameters, and the other one is a set of emerging fields, if we would call them. So of course, the emerging fields you don't know a priori. That's the reason you have to do either sophisticated theories or numerical simulation, because numerical simulation helps you seeing what is going to emerge and what kind of order parameter and what kind of description you should use at the macro level. And it's absolutely not trivial. Again, in simple systems like, for example, fluids, we know that the macro description is in terms of density and velocity, and the equations are the Navier-Stokes equation. But in many systems, it's far from obvious what is the emerging order parameter or the emerging field that you want to focus on. If you're speaking about parameters, which are the ones that describe that define the model, then the ones that are going to play a crucial role, as I've just mentioned, are not at all obvious either. And you have to experiment and see, well, and that's what we did. Out of the 7 parameters, we played, and some of them didn't seem to have any role at all, or very marginal, and others were leading to very strong discontinuities. And so the idea, if you want, okay, so this might be very technical, but the idea is that in the space of parameter, you can define a kind of Hessian, a kind of matrix that gives you the directions that are most relevant, in the sense that when you change a little bit a linear combination of the parameters, you change a lot the observation. And so by making this idea of following the Hessian systematic, you're able to reduce the dimensionality of your problem efficiently. I'm sorry, it was a little technical at the end, but...
Jean-Philippe, yeah, this is beautiful, but then, of course, we all would like to relate these phase diagrams that you showed to what happens in our world. Assume I'm a Minister of Finance of some country, which I'm not, of course. I certainly want to avoid the endogenous crisis. What should I do? In other words, are your simulations producing a qualitative phase diagram, as you said, or can you imagine that in the future, with large-scale simulation, with, let's call them artificial intelligence, you can go to a level at which this qualitative diagram could become a real diagram on which an economic ruler could try to manage the policy?
You know, I wish it will be the case. I'm not sure. I'm not sure. Really, to say the truth, I'm not sure. I don't know if we can go beyond the level of scenarios and qualitative phase diagrams. But with the emergence, as I said, of a lot of data of what people do, because we know we're observed all day long. I mean, every one of our action is recorded somewhere. So it poses other problems, you know, about freedom, about how much do we want. So maybe if it's anonymized and statistical, maybe we're okay with that. And this is already the case, you know, when you want to choose your direction and you ask Waze to tell you what's the best road that you should take, well, there's already the information of other people jammed on that street rather than that street. So we have a lot of real-time information about what people do. And so maybe at the end, it's going to be indeed possible to have precise predictions. But I don't know, because also the problem is so complex, and we have this issue that I mentioned, that, you know, even probabilities may become random in somehow, that maybe we should just be happy with not missing scenarios. So again, you know, what our little model here showed that is maybe obvious is that there's a level where you don't need to do anything and the economy will recover, but be careful, because if you trust standard models, you will be completely fooled into thinking that the economy will recover anyway, and that, you know, laissez-faire is an option. But I think intuitively people know it's not the case. So it's nice to have a model where you can actually show that it is not the case. And if you let things behave naturally, you will go into this L shape where the economy does not recover at all. And so the fact that you can save the economy by simple measures, but it leads to inflation later on, I think this is insightful. I think what is nice about agent-based models is that you can be, they're an instrument of pedagogy. They're an instrument of showing that, you know, if you make this and this assumption about how the world behaves, then you should expect this and that. And this and that is not at all trivial from the rules you give. So I think it's an education matter, education of policymakers, not to be blindsided by models that are too simple. And I think here we're really getting back at what Trichet said. Trichet, at the time, actually was interested in all these complexity things, but he was really feeling bad about this, because what was happening was absolutely not what the tools he had at his disposal were telling him should happen. So again, I think if you're prepared to things unexpected, you behave better when the unexpected happen.
cliché, we are sitting at the wrong place of the phase diagram. It doesn't explain.
No, but you're telling him, well, if you don't do anything, we probably are going to end up in dire straits.
Thank you very much for this eye-opening talk. Your critique to traditional economic models is, of course, very legitimate. We know that people are not perfectly rational, do not have perfect foresight, etc. Do your agent-based models take into account some softer aspects that you mentioned are critical for assessing or predicting crises, like trust, like the interactions, perhaps peer effects or other behavioral aspects that are perhaps difficult to prove or difficult to model?
Exactly. Yes, absolutely. This is the kind of thing that we have implemented in some of the models, is this aspect of trust that can be self-fulfilling and therefore lead to crises that are totally endogenous, driven by trust.
So thank you very much to our speaker. Thank you very much also to all of you for having attended today. We also want to thank our media sponsors, Cathy Merini, and of course to invite you to continue the discussion over a small reception behind me. Thank you very much. Thank you.